Hey, welcome to another video of Chem with Com. Today we're going to be talking about gases. These are the book chapters you could read through if you want. Remember, it's from OpenStax. Um, yeah, let's get started. This is going to be a three-part series. I don't think it's going to be too long. Um, yeah, so let's get started. Just clean up my screen a bit here. All right. Gases, this topic specifically is gas pressure, kind of an introduction. All right, what is gas pressure? Well, think about this now. You're sitting here watching my video, me talk, listening to me talk. Can you feel pressure right now? I personally can't, right? But if you think about maybe going underneath, like to the bottom of a swimming pool, or if you go to the ocean or to a lake, right? Can you feel the pressure if you go beneath the water, especially when you go deeper, right? I personally can, right? So what's happening is you have that water on top of you and it's all kind of pushing down on you. So you feel the water pressure. And we're not in the water all the time, right? But we are in air all the time. And so there are air particles pushing down. And here we have a lot of water particles pushing down on us so we could feel the pressure. Here, since gases are very far spread apart, more so than water, or sorry, a liquid, right? We still have those forces pushing down on us. They're just or a lot less than what we feel when we're in water, right? There's less of them, so much less of them, so we don't feel the pressure as much, right? But it's still there. Plus, we're born in air. We grow in air. We survive in air. So we don't normally feel the air pressure, but it's still there, right? So what is actually pressure? This is the book definition. Pressure is a force exerted per unit area. What does that mean, right? So pressure equals force divided by area. So it's how much stuff you push down. So let's say we have a force of, let's see, force of right. So let's say we have a force coming down. 1 second here. Okay, like a force of, I don't know, let's say 10 kilograms, right? And that's coming down into some little point here. And then we have 10 kilograms, another force of 10 kilograms. But now it's shaped differently, right? Let's turn it upside down, right? This is the ground, this is where we're measuring at, right? These points right here. Well, a smaller area is going to have a bigger pressure, right? Small area, big or large pressure. Big, large pressure, right? More pressure. Or greater, I guess. So we should say here large area, small pressure, smaller pressure. Right? So it takes two things. It takes some sort of force over some area, right? That's what pressure is. Okay, so if I push my hand against the wall, that's some sort of pressure, right? Because I'm exerting a force over some area. So a lot of different things. All right, so mass contributes to pressure. This big old elephant, 14,000 pounds, right, per elephant. That's what this means here. This skater should be, I don't know, looks like 120 pounds per skater. But force is mass times acceleration. So the greater the mass, right? the greater the pressure. So here we have a 14,000 pound elephant. The area is a little different, but we see that it's about 14 pounds per square inch for this elephant. It's estimated, right? This smaller human footprint, literally, and for this problem, 2 pounds per square inch. So a lot less, right? You can kind of imagine that an elephant would exert more force and more pressure than a human, right? But now let's take that human and put it on ice skates. What happens is the ice skates are kind of angled like that, right? So it's a very, very small area for those skates. And just by doing that, it increases the pressure, right? So again, it's pressure equals force over area. And we're not going to need to use this equation much, but just want to let you know. And then force, it requires mass, right? Without mass, you can't have force, right? You have to have mass. So what about atoms, right? We learned back in chapter 2.3 that atoms have mass. And gas atoms have mass, solid atoms have mass, liquid atoms have mass, right? They all have mass. And atoms are always moving. There's not many places in the universe where atoms aren't actually moving. They might be vibrating or doing stuff, but they're always, almost always moving, right? So here, then we have our mass and our acceleration, right? Our movement. And what happens is that is contributing to the gas pressure, right? That's what we're feeling. We're feeling the gas, since pressure is force over an area and force is mass times acceleration, right? We have moving particles with mass to create force, and that force is over a certain area, and that gives us the pressure. That's what we're feeling pressure, right? So we blow up a balloon, we're injecting air or gas particles into the balloon, and those particles are bouncing against the balloon and each other, and they're doing all sorts of funky stuff, right? Because there's so many atoms or molecules that make up gas because um, they're so small, right? So to fill a balloon would take a tremendous amount of atoms. So those atoms are all banging around that balloon inside to each other on the walls of the balloon. That's why the balloon inflates, right? Because those gas particles are pushing against the sides of the balloon. And again, they have mass. So we're all under pressure, right? All day, every day, we feel the pressure from all of the gas particles in the air, and it's crushing down on us. Not crushing, but and the atmospheric pressure is equivalent to about 14 pounds per square inch. So 14.7 psi. A very common unit we use for this is atmospheres. So at sea level, we're about 1 atmosphere, and that's equal to about 14.7 pounds per square inch, about equivalent of a good sized bowling ball, right? On your thumb. That's what it feels like, right? But we're used to it, so we don't really notice it. All right, so pressure has many, many different units. And if you look, these are all conversion rates, right? Remember what we talked about before. Conversion rates have to have a number, a unit, an equal sign, a number, and a different unit. And all of these are conversion rates. This one doesn't really say. Um, it's not really a conversion rate, but this is a conversion rate. This is. And then this is actually the calculations we use in class. They're going to be equal to, sorry, it should be 1 torr. 1 torr, right? So all we're going to use these conversion rates to convert stuff because the problems need conversions. All right. So remember topic 6, dimensional analysis, how to convert anything in the world. It's a quick review. Again, we want a number or a value. We want a unit, an equal sign, a number, and a unit, right? So how to convert anything in the world in 3 steps. So let's say we have this problem, convert 327 grams to kilograms. Well, first step, find the conversion rate. I look it up and you're 1 kilogram. And I know I keep saying this, and this is review, but again, you have to have the number, the unit, the equal sign, the number, and a different unit. Second step, write conversion rate as fractions. So we just, we put the 1,000 grams on the bottom, 1 kilogram on top, then we write the other one. Step 3, multiply what you're trying to convert by the fraction. So the very, very, very important part is you're going to use the fraction that has the same unit as the original value on the bottom of the fraction. So our original unit is grams. So we want to use the fraction with grams on the bottom. Because when we do 327 grams times 1 kilogram over 1,000 grams, the grams cancel out and we're left with kilograms. So the answer is going to be 0.327 kilograms. Again, if you need practice, go back to topic 6, dimensional analysis, and you can get your practice there. But we're going to use this to walk us through the next problems. All right. A typical barometric pressure in Kansas City is 740 torr. What is this pressure in atmospheres, millimeters of mercury, kilopascals, and in bar? I'm going to start labeling these so we can find the conversion rates over here on the right side, right? So we want to go from 740 torr to atmospheres. So here I can see we have 1 atmosphere equals 760 torr. All right, part 2, millimeters of mercury. So here we're going to have, atmospheres. Yeah, so we're going to go from torr to atmospheres. So we're going to use this little squiggly line means it's almost the same, but in this class, we're going to say it's equal to. So that's our second one. Then we're going to go from torr to kilopascals, right? So where else you're going to do, this is for equation 3 and then equation 3. We need 2 of those. And then bar, we're going to need this one. So we'll say, looks like we're going to need this equation or this conversion rate for a lot of them. All right, so let's go. Let's try it out. All right, so the value I'm trying to convert, 740 torr. I'm trying to convert to atmospheres. Here I see atmospheres and torr. I know that torr has to be on the bottom because that's what I want to cancel out. So let's do that. Cancel, cancel. So it's 700 and the units are ATM. So 740 times 1 divided by 760. Let's do that. 740 times, times, open parentheses, 1 divided by 760 equals 0.973, let's say 0.974, all right? So we'll say 0.974. We only have 2 sig figs here, so we'll have to report it as 0.970 ATM. All right, I'm going to label this as 1 because it's the one we're doing. 2, let's do this one next. All right, 2 is going to be 740 torr. And we're trying to convert millimeters of mercury, or 2 millimeters of mercury. All right, and we know it's a 1-to-1 ratio. or it's a 1 millimeter mercury to 1 torr. So we're just going to write 1 torr here because we want to cancel out the torrs. 1 millimeter of mercury. Torr cancels out, and we're left with 740 millimeters of mercury. The second one. Two sig figs, two sig figs. All right. Problem 3, or question, part 3 of this question. Kilopascals. Well, if you look, we do not have a conversion for kilopascals. So let's write this out. I like doing it this way if I have a two-part conversion. I'm trying to go from 740 torr to kilopascal, so kPa. I do not have a direct conversion on this table. Maybe you do. I do not. So I'm going to have to go from torr to pascals to kilopascals. So I'm going to label this as a part A and part B conversion. So I'm going to have to do two conversions. Let's try this. 740 torr. All right, conversion A is going to go to pascals. So I know it's 760 torr on the bottom. And it's a little congested up here with all the writing, but I'm going to start it. And it's 101,325 pascals. All right, so now what I'm going to do is I'm not going to stop, but I'm going to pause and cancel out units to show you what's up top, or what's on top now. 101,325 pascals is on top. So now we need part B. So this is A, and then this is B, right? This is the A conversion rate. This is the B conversion rate. So here we see that 1 kilopascal equals 1,000 pascals. Now let's cancel out what cancels out. Pascals and pascals. Now we're left with kPAs, which is exactly what we want. K, lowercase k, capital P, lowercase a. So let's do the math now. And we got to go to our calculator. Oh wait, where's our online calculator? Online scientific calculator. Let's use this one. All right, it's going to be 740, so 740 times, open parentheses, 101,325, 325, divided by 760, and then move the arrow over a little bit, close parentheses, times, open parentheses, 1 over 1,000. So 1 divided by 1,000, move the arrow over, close the parentheses, and that's our number there. 98.66. So we need two sig figs, so it's just going to be 99. So this is now 99 kilopascals. All right, part 4 of this problem, bar. How do we get to bar? Well, bar is here. And they say 1 bar is 100,000 pascals, right? So let's move some stuff around. Let's start with, actually, you know what? Let's just start over because I want to show you how I would do it without knowing this previous number here. So let's just start fresh. Torr, and we're trying to go to, what does it say? Bar. We don't have a direct conversion, so we're going to go from torr to pascals to bar. I'm going to call this C and D, so we can kind of keep track of what we're doing here. So C and D. All right, so we'll start with 740 torr. Over here is C, because we have the 760 torr on the bottom. And then we have 101,325 pascals, right? Pascals. And then we're going to go to number or letter D over here because we want to go to bar. So it has to be 1 bar up top and then 100,000 pascals. Let me clean that up a little bit. Okay, let's cancel out the cancel out stuff. Torr cancels out. Pascals cancel out. We're left with bar. It's exactly what we wanted. So again, if you do the units, it kind of double checks it for you. All right, let's do this math. Let's go to a different calculator. 740. So let's clear this. 740 times open parentheses. I think it's 101,325 divided by 760, close parentheses, times, I believe it's open parentheses, 1 divided by 100,000, close parentheses. Let's double check. 101,325, 760. Let's try it. Okay, 0.9865. So let's say 0.99. Oops. Go back to my 0.99. So we could have went from kilopascals. Sorry, let me just finish this bar, right? We could have went from kilopascals to pascals to bar, but I wanted to take you through this way, right? So we could have done that. It would have been the same number. All right. Well, that wraps it up, and I will catch you next time on the next video. And it's going to be part 2 of gases. All right. I'll catch you later.